Hey everyone, today I am going to discuss how the Schrodinger wave equation is derived. The Schrodinger equation is all about energy. From it, we can find the different energies a particle can have. All particles have discrete energy levels. We use the Schrodinger equation to help us figure out what these energies are. So, this is the Schrodinger equation. Looks pretty complicated, right? Well, let's break it down. Let's first look at kinetic energy, which equals p squared over 2m, where p is the momentum and m is the mass of the object. It is important to know that particles can be thought of as waves, on a small scale at least. To help us understand that, we use de Broglie's equation, lambda equals h divided by the momentum. H is Planck's constant. It is very, very tiny. Because it is so small, Planck's constant is used for small particles, such as protons and electrons. However, for the kinetic energy equation, it is more useful to talk about h bar in wave number instead of h in wavelength. How do we change it? We simply multiply the momentum by 2 pi over 2 pi, which is 1. This gives us h bar, which is the reduced Planck's constant. Wave number is 2 pi divided by the wavelength, lambda. Okay, so now we have our new kinetic energy equation, h bar squared times k over 2m. Now let's look at wave functions, which are used to encode information about waves. Wave functions are called psi and look something like this. This e to the ikx is just another way of writing sines and cosines, and waves are just made up of sines and cosines. I know it looks confusing, but there is a reason the wave function is written this way. If you differentiate it, you get the same thing multiplied by the differential of the argument. We can do this again to get negative k squared e to the ikx. This is an eigenvalue problem, where this is the eigenfunction and this is the operator. An operator just means that it acts on something. This extra part right here is the eigenvalue. Now, with what we know about kinetic energy, the wave function, operators, and eigenvalue functions, we can make an operator for kinetic energy. For now, let's just assume that there is no potential energy. Next, we can add the wave function, which is represented by psi, which allows our answer to be more precise. We can add in our k squared that we generated from the wave equation, which is negative. Notice how this is a partial derivative instead of a total derivative. This is because there is more than one variable in the function. Yay! So now we have the one-dimensional, time-independent Schrodinger equation for a particle not in a potential, which is 1D TISE in free space for short. Unfortunately, this equation is very specific. If we add potential, making the equation more general, we will be able to use the equation in more circumstances. Let's start with time. So the energy of a photon is h times f, where f is its frequency. We can multiply by 2 pi over 2 pi again to get this in familiar terms of h bar and omega. For this equation, we are assuming that this holds true for particles as well. Thankfully, our assumption is correct. Keep in mind, this energy is not added to kinetic energy. It is just another way of finding total energy of the system. Because there are going to be sets of energies, we need to know the eigenvalue equation, but this time to generate an omega. If we look at the wave function again, we see an omega in the exponent. To pull it out of the exponent, we just need to find the first derivative in respect to time. Don't forget to add I. Awesome, we found the time-dependent Schrodinger equation. But don't celebrate too fast. We're not quite done yet. This equation is only in one spatial dimension. It is therefore not very useful for applications. We need all three spatial dimensions. It is not hard to add this. These three dimensions do not interfere with each other, so they can each contribute to the total energy separately. With all three spatial dimensions, the wave equation becomes this, and the time-dependent Schrodinger equation becomes this. This can be simplified by adding the Snabla operator, which adds the three different second differentials. We also need to add any terms due to the potentials the particle may be at. This is called v, which can depend on any combination of x, y, z, and t time. Because this varies from problem to problem, we just add the general form into the equation. This is called the Hamiltonian operator, h hat. This is equal to the total energy. And now finally we have the full Schrodinger wave equation.